Okay, let's start today's session. Good evening, everyone. My name is SHAKSHI Bhardwaj. I am a PhD scholar under supervision of Professor Pradeep Kumar Maji, Department of Polymer and Process Engineering, IIT Roorkee. And I am a course coordinator for Polymer and Process Engineering course under Professor Shishir Sinha in Chemical Engineering Department, IIT Roorkee. And today we are going to take questions related to assignment 6, which is Chemical Reactions and Engineering. So start with the basic introduction of mine. As I already told you, I'm SHAKSHI Bhardwaj. I'm in Department of Polymer and Process Engineering in Indian Institute of Technology, Roorkee, and I'm doing PhD on the topic fabrication of cellulose-based aerogels for thermal management applications under the supervision of Professor Pradeep Kumar Maji. Apart from this, I have completed my master's from Maharshi Dyanand University and from my bachelor's from Kirodimal College. And also I've conducted two projects, one in Indian Institute of Technology, Roorkee, over lightweight thermal superinsulating aerogels, and another one in University of Delhi over repurposing of drugs for SARS-CoV-2. So in the last session, we have taken questions related to mass transfer. And in the session, we already discussed about the mass transfer and related different phenomena. But as we have already discussed about that, in this session, we will take questions related to polymers or the mass transfer phenomenon. And I have some gone through the topic and found out some that mostly all the topics of mass transfer like Fick's law and the numbers we have read in the last class have the similar concept with the polymers itself and with the other materials itself. All of the questions kind of similar, but here we have taken some questions which are a little bit different. So starting with those questions first, and then we will start with the different topic. So here's the first question, which is diffusion through a semi-crystalline polymer is generally faster than amorphous polymer, slower than amorphous polymers, independent of crystallinity, and not possible at all. So we have read about the diffusion of a through a semicrystalline solids or polymer gases in the last session. Here we are talking about the polymers, and which is kind of similar definitions all those things have. But because we are reading about the semicrystalline and amorphous polymers, so I want to tell you like semicrystalline polymers are which are having crystalline regions, and amorphous polymers which are randomly arranged, which do not have the crystalline regions. So diffusion in which of these is faster? Taking 1 or 2 minutes so you guys can answer or understand the topic. Okay, I just got one answer, which says it's faster than amorphous polymers. Okay, let me see. Okay, then if no more answers, so let's go with the solution. And yeah, it's not A, it's actual B, which is like slower than amorphous polymers. And the reason is because semicrystalline polymers, just a second. Semicrystalline polymers are like highly crystalline ordered polymers, and due to that highly crystalline, they are tightly, and due to their tightly packed structure, they have literally very minimum space for any of the molecule to diffuse through them. Whereas on the other hand, amorphous polymers, which have the disordered arrangement like this, have more free volume, more space, and diffusion through amorphous polymers is easier as compared to semicrystalline polymers. And that's the reason. Diffusion primarily occurs through the amorphous regions because there are more free volume and flexibility. The crystalline regions act as barrier to diffusion. They are rigid and tightly packed. They do not allow penetration of molecules like gaseous solvent to easily pass through them. And that's why diffusion through semicrystalline polymers is slower than amorphous polymers. So here the correct answer is B, not A. I hope this is clear. So the next question is, the permeability of a polymer to a gas will generally increase with increasing crystallinity, decreasing temperature, increasing free volume, and decreasing polymer chain mobility. Which of these factors will help of a polymer to increase its permeability? Okay, I'm expecting some more answers. Okay, then let's move to the answer section. And yes, it's C because of increasing free volume, and that's how the permeability of polymer increase because of the increasing free volume. So what is the permeability and how it depends on the polymer? Permeability of a polymer of a gas to a gas depends on how easily gas molecule can diffuse through polymer matrix. And second, it depends on the solubilize into the polymer. So the relation between permeability and diffusivity is permeability is equal to diffusivity into solubility. So this is the formula, and on this formula also some questions can come. So it's like this. The permeability of a polymer of a gas to a gas depends on how easily T can diffuse and solubilize. And there are two factors on which the permeability depends. And increasing free volumes give more space to molecules to diffuse through them. And that's why it is the permeability of a gas will increase throughout the polymer matrix. It's a simple concept. I've taken these two examples particularly because they are a little bit different from what we have studied in the last session. But most of the concepts what we have cleared is kind of same to a polymers also. So I am not going into the depth of that, and I'm just concluding the particular topic here, and we'll start the next topic, which is today's topic, which is the rate of the reactions and different polymerization reactions, which we will going to study in the upcoming slides. Okay, then let's start with the topic. So yeah, polymerization reactions, and basically these are the reactions which helps monomers to get into to form polymers, and there are like many processes by which one or two monomers can produce different type of polymers. So here are some characterization or some classification, which is like polymers can be classified into two. Polymers can be classified into two. First, one is step growth and another one is chain growth. In step growth also there are two type of polymerization. One is polyaddition, one is polycondensation. And in the chain it is like four type of polymerization reaction in radical, cationic, anionic, and coordinative polymerization reactions. So what are these kind of polymerization reactions? These are the reactions which we are going to study in the depth in coming slides. So starting with the basic idea of these polymerization reaction. So first is the step growth. In the step growth, there are two different type of monomers, and in that case, both of the monomers can react or have some reactive groups or some functional groups which can react together. And in the step growth, there is like the elimination of a small molecule like water or ammonia happens generally when two monomers react, and they can form this type of polymeric chain. And the termination in the step growth polymer is like either one of the monomers should have, we need to add some of the monomers which have only one functional group, because in that case of step growth polymerization, we generally use difunctional groups. Like A, if A has functional group from here also, from here also, and B has some functional group here also and here, so that they can react with them and they can also react with these sides. And if we add just simple the functional monomer with the one AND group, it will react only from the one side, ending the chain polymerization reaction. Such type of termination can happen when we add these type of monomeric unit in the step growth polymerization. Another one is chain growth polymerization. And in the case of chain growth polymerization, initiator is added to a monomer because monomer cannot react itself on its own. So we need some initiator to initiate the monomeric and monomers, and then it can propagate throughout the one monomer is initiated from this initiator, then it will initiate the another one, that it will initiate the third one, and so on. So it's like the polymer chain continues. And in that case, the termination happen when two such kind of monomers, like one initiator like this chain and another chain like this chain, when these type of chain collides, and these can form a bond. So such type of termination can, and many type of termination can occur in this chain group polymerization, because at this point, one single monomer could also react to this initiated polymer, I can say, and also the initiator also can react to this position. So many type of termination can occur. Either two big chains can collide with each other, either one chain can collide with the monomer, either one chain can collide with the initiator itself. And the last one is the radiation polymerization. In this case, the radiations like gamma rays, alpha rays, not alpha, sorry, exactly, X-rays, gamma rays, UV rays, which helps monomer to get initiated and to release some electron and form a radical itself. And then this radical will help the other polymers to polymerize and to form the long chains. So they are some type of polymerization reactions which we will study. And I hope this basic table of polymerization reactions and basic idea is clear to everyone now. And if not, you can just write me in the chat box. I will explain any of if you didn't understand. And if not, then we will move forward with the questions. I did not get exactly the difference. Okay, so here's the trick. You want to get the between step and chain. Okay, so there is like chain and step. In the step polymerization, the basic difference I can say in one word is like the removal of a small molecule like water, H2O, or NH3. If two monomers react and a small molecule like H2O or NH3 release, then it is the case of step growth polymerization. And in the chain growth polymerization, no small molecule will release from there. Rather, we need an initiator or a molecule which initiates the monomeric reactions. For example, in the step growth, you have seen the example of nylon 6,6. I'm taking an example here. So in the case of nylon 6,6, we have adipic acid, yeah, and we have a hexadiamine. And both the cases, I'm just writing hexadiamine as HT. Okay, so we have this acid which have the acidic group COH, and we have this hexadiamine which have the basic group NH2. And when then COOH and NH2 react, so what happen is a formation of a amide bond CONH2 with the release of a water molecule. And this release, we generally know these kind of reactions as condensation reaction. You have read about the condensation reaction, I guess, and these are kind of condensation reaction. And this is a example of step growth. So you can say step growth. In the step growth, these kind of reactions happen when a small molecule releases, or they have monomers have the functional groups. In the step growth, monomers have the functional group. In the chain growth, monomers do not have the functional groups. Rather, like aniline or ethylene, simply we can say like CH2, double bond CH2. So such type of monomers are required to form polyethylene. But here it cannot react on itself because it do not have any functional group. So it need an initiation, and that's for that we need to add an initiator, or that's why we have like radical, cationic, anionic. So the initiator could be radical AIBN, in which this N double bond N is present, and this will break, and there was the N radical generated from there, and which initiate the reaction. So in that case, the initiators are required, and the other difference is no small molecule release in that case of chain growth polymerization. So I guess this is the basic difference you got to know, and if not, in the further slides we will read in the more depth, I can say. Okay, so moving forward. This is the first question. A distinguishing feature of chain growth polymerization compared to step growth polymerization is. Right now is what your question is, like whether there is a difference between chain growth and step growth. So the options are: all monomers react at once in bulk. In the chain growth, monomers are always bifunctional. Polymer chains grow only at reactive centers, and byproducts like water are released. So they are asking about what is the distinguished feature of chain growth as compared to step growth polymerization. Okay, polymer chains grow only at reactive centers in chain growth. Let's see the answer then. So yeah, at C it is correct, like polymer chains growth, because what have we just have discussed in the chain growth polymerization, we need reactive centers, or we need such type of initiators which can create reactive centers on monomers like these. And if we look at the other options, like all monomers react at once in bulk, this is not a correct option because all monomers cannot react once. It need, or I can say it will take time for monomers to get initiated by initiator and then react. The second option is monomer are always bifunctional. No, that's not the case. It is the case in the case of step growth polymerization. There, the monomer should be bifunctional to react. Third, the polymer chains grow only at reactive centers is true. And the byproducts like water, no. Byproducts like water release in step growth, not in the chain growth. Chain growth, there is no byproduct which release. And yeah, this is the mechanism which I'm talking in the last slide, like there's a mechanism, and you can see it's a monomer and it is inactive. So it needs an initiator which have a reactive side. So this is the reactive side, and what happens is that it will initiate, it will create the reactive center on the monomer itself. So the structure should look like this. Like this is the initiator, and this created the reactive center now on the monomer itself. And now this reactive center will attract more monomers to it and form the reactive centers. So like that, the chain growth 1, 2. Now this monomer will get react to there, and the reactive center will create here. So the chain grows like this. So here in the case there is no byproduct. It's just one monomer getting the reactive side from the initiator, and that it will create the reactive side on the other monomer. So it's the chain growth. So like the chain grow slowly like this. I hope the chain growth polymerization is now clear, like what happens in the chain growth polymerization. And this, the initiator could be a radical, could be a cation, could be an anion, or the radiation itself. So this kind of initiators which we use in the chain growth polymerization. And that's how their names is different, like cationic polymerization, anionic polymerization, free radical polymerization, which is a part of a chain growth polymerization. Okay, I think it's clear. Okay, let's move forward to the next question. If you get any doubt, just drop me a message in the chat box. I will repeat it. So the next question is, which of the following best differentiate polyaddition from polycondensation within step growth polymerization? So in the last slide here, we have seen that step growth is divided into two. One is polyaddition, another one is polycondensation. So the question is about what is the difference between these two, polyaddition and polycondensation. So the polyadditions, the options are first, the polyaddition require an initiator. Second, the polyaddition release a small molecule as a byproduct. C, the polyaddition form bond without byproduct. And D, polyaddition occurs only in the gaseous monomers. So what is the polyaddition in the step growth polymerization? Okay, I got mixed answers. It says first, polyaddition form bond without byproduct, and its polyaddition form occur in gaseous monomers. So I can say the correct answer is C, which is polyaddition form bonds without byproduct elimination. I know this statement contradict what with the statement what I have given earlier with the chain growth and step growth, because I have told everyone that step growth polymerization, a byproduct is released, and in the case of polyaddition, I am saying that byproduct is not releasing in that case. Yes, this is in kind of a different type of step growth polymerization. The example of these kind of polymerizations are here. So first, this is the polycondensation. Like see, in this case, two functional groups are there. So the major difference between chain growth and step growth you need to realize is in the step growth, there are always functional groups, but in the chain growth, there are no functional groups that need to be initiated. And here also we have two functional groups, which is COOH or OH. And in that case, this OH and COOH will react and will form an ester bond, which is CO double bond O. And with the elimination of a water like H2O, so with the elimination of this water molecule like this, it form a ester bond. It form a ester bond, and this ester bond is a kind of a condensation reaction. So condensation generally happens when there is a release of molecules like H2O or NH3. But here we are asked about the polyaddition polymerization. So in the case of polyaddition, the rule of having functional groups is still the same. So here also in the later case, you can see the polyurethane formation in which there is the monomer has OH groups and the other monomer has the OCN groups, isocyanate groups. So what happens in that case? it is because of those two functional groups the monomers are reacting to each other. But in their case, there is no byproduct elimination. They're like water and NH3, that no byproduct is eliminating. Rather, they are rearranging themselves, and these two groups are rearranging themselves, and formation of this happens. So here's like C O double bond O N H, and this happens on the rearrangement. And this is this is the basic example of polyurethane formation, in which one is having the diol and other one we have the isocyanate. So these kind of reactions happens, and they are named as polyaddition, and which is a part of step growth, not chain growth, because such monomers do not require any initiator to initiate them. They have functional groups, so they can react by themselves, but it is not like the byproduct is releasing. So it's a part of step growth, and here in the step growth, it's known as polyaddition. I hope this is clear now, because what is the chain growth, what is the step growth? In the step growth itself, what is polyaddition and what is polycondensation? And if not, I can just repeat whatever I said again. But this is very important and a topic, because generally this create confusion, because in the case of addition type of reactions, they happens generally in the chain growth, and condensation happens generally in the step growth. But it is a general term. Polyaddition is also an example of step growth, because the formation of polyurethanes where or some more polymers where no other byproduct is releasing is also an example of step growth. It's just I have said the basic requirement is functional group, or the group which can react by themselves without. Okay, what is the question? Oxygen is in the polymer side. The oxygen with double bond is connecting with it. Okay, so if it is creating issue, it is C. It is carbon. It's just a representation. So they have not representing the carbon and form a chain like this, but this is not a chain. This is the C bond. C is there. So if I write by myself, it is, in the first case, it is the ester group, which is C double bond. Here the R is present. Here also R is present. So this is the ester bond in this case. Whether in this case, this is also the rearrangement, and it forms O, C double bond O, and NH. These kind of linkages with the monomers. So it is C. Do not confuse that it is not. So yeah. Okay, let's move forward with the next question then. Which factor does not affect the rate of step growth polymerization significantly once monomer conversion is high? So now we are moving forward with the different concept, which is the rate of the reaction. So here we are asked about the which factor does not affect the rate of step growth polymerization when once monomer conversion rate is high. Functional group reactivity, temperature, catalysis present, and initiator concentration. So which of these factors will not affect the rate of step growth polymerization? Okay, I got two answers. One says functional group reactivity and another one says initiator concentration. So it's like the which. First, the question is about which factor does not affect. So they are asking about which factor does not affect the rate of step growth polymerization. So for the step growth polymerization, we have read that step growth polymerization should have functional groups, of course. And the reactivity of functional groups and group is an important aspect in the case of step growth polymerization, because as long as the functional groups are very reactive, they can react very fast and the polymerization gets fast very easily. So A option should be like it's the factor which is affecting. So it does not affect, it's not the case. For the B and C options like temperature and catalyst, so yeah, they are also they can also affect the rate of step growth polymerization, because temperature, whenever we increase the temperature, the reactivity of molecules will increase generally, not in every case. And third, the catalyst, if we add any catalyst to increase the reactivity of functional groups, so the generally the monomer conversion rate will also increase. Only the D, which is the initiator concentration. So we have discussed that step growth polymerization do not require any kind of initiator. Rather, initiator required in the chain growth. In the chain growth, we require initiator. So here, there, the initiator concentration will play a role, not in the case of step growth. So this is the only factor. I just by mistake I wrote this. It's the D. It should be. It's not D. So the D option is correct, which is the initiator concentration, which do not require in the case of step growth polymerization. And the reason is the step growth polymerization proceeds through reactions between functional groups on the monomers or oligomers like OH, COH, NH2, NCO. These kind of functional groups they have. It does not require initiators like chain growth polymerization. So once the polymerization underway, especially at high conversion rate, the rate is primarily governed by how quickly these functional groups can find and react. So thus the functional group reactivity plays an important role. Of course, temperature also plays an important role. The temperature, increasing or decreasing temperature can affect the reactivity of functional group and of course the polymerization reaction. Catalyst can also play, because once the catalyst should be added, the reaction rate will increase. But initiator concentration do not have any impact on the step growth polymerization. Okay, then if it is clear, moving forward with the next question. Which situation would most likely result in premature termination of step growth polymerization? So here we are asked about the termination. So like which of the factor is helping in the termination of steps step growth. And of the options are presence of monofunctional impurity, high monomer concentration, high vacuum to remove byproducts, and increasing reaction time. So which of the following option will help in premature termination? Okay, I got two options which says it's A, presence of monofunctional impurity. And yes, the correct answer is A. And how presence of monofunctional impurity will affect the termination, because we have read that in the case of step growth, monomer should have functional group on both of the sides, which it can propagate either through this side, either through this side. So if we add such monomers which have only functional group from this side, it will not propagate from this side, and ultimately whenever it react to any of the monomer or polymeric chain like this, So it simply terminates the chain. So such kind of monofunctional impurity, if we can add, that can happen and that can cause premature termination. Rather, high monomer concentration will not affect the termination, rather it will affect the propagation. High vacuum to remove byproducts. If we are removing byproducts at the same time it is forming, so that helps the reaction to go smoothly of unnecessary and would not create unnecessary impurities in the reaction media. Increasing reaction time. If we increase the reaction time, the large polymer chains like that forms very easily. So the only option which most likely result in premature termination is presence of monofunctional impurity. The monofunctional impurities such as ROH, RCOH, or other monoreactive compounds can react only when one end of a growing chain. Only they can act as a cap, and they can cap the chain and making it unable to grow any further. So these results in premature termination, prevent high molecular weight formation. So this is how we can control the rate of reaction here. I hope this is clear. Okay, then let's move forward with the next question. In chain growth polymerization, high molecular weight polymer is achieved. They are asking about chain growth polymerization and why high molecular weight polymer achieved. Only at high conversion, even at low monomer conversion, only after initiator is depleted, only in the presence of catalyst. How high molecular weight polymer is achieved? Okay, I got mixed answers in this case as well. Like one says it's B, even at low monomer conversion. One says it's A, which is only at high conversion. So here the correct option is, I don't know why. Sorry, I just got confusing option answers. Maybe I didn't check it through. It's the B, even at low monomer conversion. And why it is so? So it has the reason behind this. This is the graph which says how the polymer conversion will take place in chain growth and step growth. So here, polymer chain grows rapidly by successive addition of monomers to an active center, example, a free radical, carbocation, and carbanion. So only a chain is initiated, it propagates very quickly, forming a long chain in a chains in a second or a millisecond. Therefore, even if only a small fraction of monomers have reacted, overall, individual chain can already be very strong. So what they are saying is, in the case of chain growth polymerization, the initiation help have with initiator molecules and which can initiate the monomers, and that monomer chains will propagate at very faster rate. So they are like, once the chain is initiated, it propagates very quickly, forming a long chain in seconds or in milliseconds. So what happened in the reaction media is, at first small molecules like monomers present in the reaction medium, and we add some initiator in that. So at first all the initiators will initiate the monomers, and because of the low monomers, low molecular weight monomers, they can react at a very faster rate. But what happens with time, like at a particular position, when the monomers chains reacted and form a long chains like this, and then these kind of long chains present in the reaction medium. Now, what happens is this, if you look at the graph, in the millisecond, the conversion rate has become like 90 or more than 90%, or whatever the percentage is. And then it will act as a constant for a longer period of time. And that happens because of the long chain polymers, or I can say because of very monomers react to form the long chains in very beginning itself. And that's how the reaction media and the viscosity of the reaction media will increase much very fast. And that's why, let us suppose this is the monomer reaction medium, and here is the monomer with the active site, and one here is the monomer with another active site. So what happens when they are just two monomers? They can simply react with each other. But when they form long chains like this, and they form the long chain like this, so it became very difficult for them to move and to react, and that's why the rate is constant for a longer period of time until it terminates. So this is a kind of the rate of chain growth polymerization happens like this. So average molecular weight and conversion percentage. So very easily the molecular weight of the monomers increases here because of the rapid formation of initiation, and then the rate will stop at a point because of the movement of polymer chains are very hard in that medium, and that's why the rate will become the constant. On the other hand, in the step growth polymerization, what happens is at very high conversion, like the maximum conversion of the monomer happen at very high conversion rate. So it's like in from the very start of the reaction until the very end, the conversion is very slow at first, and then when in the end, the conversion will increase in the milliseconds or like this at the end. And this step growth polymerization, this type of conversions happens in the law is called Carather's law, which we'll be going to read, and that define how many second or how many conversion it's required or what kind of polymers form in the case of step growth. And there in between is a living polymerization, which says it's the ideal case, like with the conversion itself, the molecular weight increase. So it's the case of ideal polymerization with, but generally living polymerization is very tough. Rather, chain growth and step growth are moved like this. So I hope this graph clearly states, and my point is clear to everyone with what I try to convey here, the rate of polymerization. So the question is like if chain growth polymerization, high molecular weight polymer is achieved at even at low monomer conversion. So very low monomer conversion, most of the polymers molecule, the molecular weight will increase. Okay, then if it is clear, if the graph is clear, let's move to another concept. And yeah, this is the question first. Which of the following best describe why chain growth polymerization typically results in narrower molecular weight distribution compared to step growth? So here they are asking about molecular weight distribution, and they are saying like in chain growth polymerization, the molecular weight distribution is narrower rather in the step growth. Why it is so? So the first option is only monomer with identical chain length react in chain growth. Second option is polymer chain grow rapidly from active centers in a controlled manner. Third is chain growth has low kinetics. And fourth is chain growth only occurs in presence of UV light. Why chain growth polymerization have lower or narrower molecular weight distribution? Yeah, I just got one answer. Yes. So let's look at the answer and the concept behind the molecular weight distribution. So the correct answer is B itself, which says polymer chain grow rapidly from active centers in a controlled manner. And why it is so? Because of the phenomena we just have read. The chain growth polymerization precedes by the growth of individual polymer chain from active sites, such as free radical, cation, or anion. Once a chain starts growing, it rapidly adds monomer one after another until termination occurs. Because each chain grows independently and quickly from an active center, many chains reach similar length and around the same time, leading to a narrower molecular weight distribution. So they are saying because of the because of each chain grow independently quickly from an active center, many chains reach similar lengths around the same time, and which can lead to narrower molecular weight distribution. Because the molecular weight distribution, which we have read in PDI also, which says like if it is near to 1, which is the narrowest, and all of the molecular chains are of same molecular weight. Sorry, all of the polymer chains should be of same molecular weight. But when the value should be differed from 1, the graph will look like very broad. And the reason behind this, like in the case of step growth, involves reaction between any two molecular species, monomer, diamers, oligomers, kind of, at any time without a specific active site controlling growth. This led to a broader range of chain length and thus a wider molecular weight distribution. So they are saying in the case of step growth polymerization, because they have functional groups between them, so they can react, like the monomers can react with the oligomers and the polymers, and it says so the chains are very much disorientated and the molecular weight are very in the many reasons, and that's why it has a wide molecular weight distribution. Whereas in the chain growth, similar type of reactions proceed with the different chains, and that's why it has a narrower molecular weight distribution. I hope this concept is also clear. So, like in every question, we are taking a different concept here. It's not the repetition, and that's why this today's session very important, because it clearly states as polymerization reactions, and which is an important part of a polymer and process engineering course. Okay, then let's move forward. Okay, has the concept which says Carruthers theory, and I specifically told you in the step growth polymerization, the rate generally follow the Carruthers theory. So, what is the Carruthers theory? So, Carruthers developed a simple method of analysis of predicting the molar mass of polymer prepared by step polymerization. So, generally, how much monomers react to form polymers, and what is the molecular weight in that case, which we can determine with the help of Carruthers law. And generally, it states that X is equal to N not by n, whereas n is the number of molecules present initially and n is the number of molecules remaining after a time t. So it's like the initial concentration of monomer, it's like the concentration of monomer at the time t, which gives this x. And this is not the Carruthers law, rather Carruthers equation is this xn 1 by 1p, where xn and x0 are the same, like the number average degree of polymerization. And P here is the fraction of functional group that have reacted. Like it's the fraction group present at the initial and the functional group present after conversion at the time t. So this is given by a fraction which is known as P. So this kind of equation gives generally the Carruthers equation, whereas this gives us the degree of polymerization, and the degree of polymerization tells us about how many monomers have reacted. So we can easily calculate the molecular weight from the degree of polymerizations, and we can calculate degree of polymerization from if this equation. So here on this equation, we will solve some questions, because on this equation there could be questions which can come, which can be asked. So the first question is, at 99% monomer conversion in a step growth polymerization, what is the approximate number average degree of polymerization? So they are saying that at 99% monomer conversion in a step growth, what is the approximate number average degree of polymer? Okay. This is a simple question. That's why, yeah. So the answer is B, which you guys already have predicted B, and which is correct. And the equation is like, sorry, and the equation is like 1, which we have read in the previous slide. N is equal to 1 upon 1 minus P. Whereas here, the 99% monomer conversion, so the value of P is given as 1 upon 1 minus 99%. If we convert percent into normal factor, it is 0.99. And when we solve this equation, it will be like this 1.0.01. And when we solve this, so it will give us 100. So the degree of polymerization at 99% conversion is 100. So the correct answer is B. And it's a very simple question. I guess you guys don't have any problem in the solving this question. It's based on simple formula. Okay, then move forward with the next question. In a step growth polymerization, what does significant molecular weight buildup occur? When does significant molecular weight buildup occur? Right from the beginning at 50% monomer, only at very high conversion, or it is independent of monomer conversion? They are asking about what does significant molecular weight buildup occur? Okay, I got answers which says it's C only with high conversion, which is 95%, which is very true. If we look at the graph of step growth polymerization goes like this. So which says at higher conversion, the molecular weight of monomer will be high. And if we go by the formula, which says it's 1 by P, in the case of 50%, which is like 1 minus 0.0, 0.5. And on solving this, we got answer of 2. While if we solve for 1 minus, which we solve in the last like 99 for 0.99, more than 95, then we will get the answer of 100. So at the 50% monomer conversion, the molecular weight we will got, it's just only the degree of polymerization we got is only 2. Whereas higher concentration, we will got the degree of polymerization higher, which is like 100. So simple, the correct option is C, which is the only at very high conversion at more than 90%, the significant molecular weight buildup occur, not at the lower concentration. So this can be confirmed by graph as well as the Carothers equation. So I hope the concept of Carothers equation and the rate of step growth and condensation polymerization too is clear to everyone. Okay, then move forward to the next question. Okay. What is the main difference between reaction order and molecularity? So they are asking about what is the main difference between reaction order and molecularity. Order applies only to unimolecular reaction. Molecularity refers to rate laws. Order refers to mechanism. Order is experimentally and molecularity is theoretical. And there is no difference. So what is the difference between molecularity and order? Okay, I only got one answer which says order is experimentally determined and molecularity is theoretical. Okay, then let's see what is the correct option. The correct option is C itself. Yes, order is experimentally determined while molecularity is theoretical. And molecularity generally depends on number of molecules or atoms or ions that came together simultaneously in a single elementary reaction and step to form the product or the intermediate. So they are like how many reactants are reacting at once. So from that we can calculate the molecularity. Rather, order is determined purely experimental. And the order of reaction we cannot determine by looking at the reaction. So in the molecularity itself, the unimolecular reaction, which says only one molecule is reacting, in the bimolecular reaction where two molecules is reacting, and in the termolecular reaction where the three or more than three reacts. I hope this molecularity and order, the concept of this is clear. And if yes, we will take one more question on the molecularity itself. Which of the following best describe intermolecular reactions? So which of the following statement describe the intermolecular reaction? Like first, common in most biological pathways. Second, occur rapidly and spontaneously in gas phase reactions. Third, rare due to low probability of free body collections. And fourth, involves a zero order rate law. So which of the following best describe intermolecular reactions? Okay, then the correct answer is C, which says it's rare due to probability of three body collection. And the reason is because third molecular reactions are rare because simultaneously collisions of three molecules are statistically unlikely. And more than three because of the collisions, the reaction rate is very, very low. Okay, then move forward to the next question. Yeah. Which mechanism is primarily responsible for initiating chain growth in UV cured polymer system? Asking about which mechanism is primarily responsible for initiating chain growth in UV cured polymer systems. Thermal, ionic, radical generation, and coordination polymer. Okay, the correct answer is yes, C, which is radical generation by photoinitiation, because they are asking about the UV cured system. They're asking about the UV cured polymer systems, and because of the UV, that is a part of photoinitiator or the photo-based polymerization reactions. And this is the mechanism for these kind of reactions in which a photoinitiator like this and provided with the light source which will form a reactive species, and this reactive species can form the monomers, can generate reactive sites on monomers, which helps the monomers to grow like this. Okay, if any kind of disturbing sound is coming, so okay, I hope these concepts are clear to everyone. And I just wanted to ask, like, if the disturbing sound is coming from outside, is it, or just I can continue like this? Okay, then if it is okay, I hope it will get away soon. Yeah. Okay, then move forward with the next topic. I guess we are about in the ending of the sessions, like some of the questions based on numericals is left, and most early we have covered. Okay, good, thank you. Okay, starting with the next question then. What is the significance of point where average functionality, which says F average, is equal to 2 in a step growth polymerization? So here is a term which says average functionality, F average. What does it mean like F average is equal to 2? So chain growth stops completely, all chains are terminated, gelations became possible, or linear polymers are the only products? Okay, I just got one answer. Okay, the correct answer is not D, which says linear, rather it's C, which says gelation became possible. So with the F average or the average functionality became 2, it is generally the case for the gelations, and we will now read about this theory where F average is what should be the significance of it. So it's the Flory-Stockmeyer theory. I'll just rewrite it. So it's the Flory-Stockmeyer theory, which says it's a statistical theory that describes the cross-linking and subsequent chelation in step growth polymerization, and where it predicts that how these kind of low molecular weight polymer transform into three-dimensional insoluble network. And this theory is based off two key assumptions. One is that functional group are of equal reactivity regardless of molecular size. And the other one is intermolecular reactions, which can form rings with the single molecules, are negligible. According to Flory-Stockmeyer theory, it says that gelation the gelation and the formation will occur when F average is more than 2 or equal to 2. Like if average become equal or more than 2, then it is the likely the case for the gelation. And this is the critical point beyond which the branching became sufficient to allow for an infinite network to form. As gelation begins, the average molecular weight tends to infinity. Since the system transition from finite molecules to cross-linked macroscopic network. So if F average is equal to or more than 2, generally it's the case for gelation. In the case of step growth polymerization, so it's the C, and this is the concept of F average, average functionality. Okay, then let's move forward with the next. Okay, so we are now at the orders of reactions. So it's the kinetics of the reactions, and we have read this type of kinetics in the chemistry, where it says the reaction order could be 0, first, second, and third, and so on. And the rate equation for the zero order reaction, it just depends on the rate constant, which says a scale, not on the initial concentration of the reactant. Whereas in the first order reaction, the rate of reaction depends on K, and A is the initial concentration of A. And in the second, it will become A square, like this. So if we look at the rate laws, so in the zero order, it is A is equal to A naught minus KT, whereas A is the reaction of a concentration of reactant at the time T. A naught is the initial concentration of reactant, K stands for rate constant, and T stands for time. There are different kind of rate equations for all of different reaction orders. Like in the case of first order, it will depend on it's exponential E minus KT, whereas in the second order reaction, this KT factor will in the denominator of this. And if we look at the units of this rate constant here, so for the zero order rate constant, the unit of rate constant is mole per liter per second. For the first order, it is only second inverse. It will not depend on the concentration of reactant molecules. And for this, it will the reverse of this. That is liter mole inverse. And if we look at the graphs, so if we look at the zero order rate, so it is it is not dependent on the concentration, so it is a constant throughout this. First order will depend on the concentration equally, so it's a linear kind of thing, and the second order, it is because of the square, the graph should like this. And if we look at the concentration and time graph, because concentration with the time increasing time, concentration became like this. In the first order or the second order, this will decrease exponentially. And if we look at this, the concentration and the time depends on each other. Here's the E factor which involved between the time and the concentration, and it is inversely proportional. So kind of these the graphs come for these type of rate orders. And based on these equations, we will now solve one or two questions, I guess. So the first question is, the reaction follows zero order kinetics with a rate constant of 0.25 mole per liter per second. How long will it take for the concentration to drop from 2.0 mole per liter to 0.5 mole per liter? So they are asking about time, and they have given us the rate constant, initial concentration, concentration at time t. So it's a very simple question. We just need to put the values in the formula, and it will take us that time. And the formula of this is A is equal to A naught minus KT. So just by putting the values in this formula, we can calculate the T. Okay, I got one answer which says it's A. Sorry, and yes, the correct answer is A because for the concentration at time, it says the concentration dropped like 0.45 at that time. Initially, it was 2.0, the rate constant is 0.25, and we need to calculate the T. Simply by solving the formula, the T value is equal to 2.0 minus 0.5 divided by 0.25. And just simply solving this, we will get the time, which is 6 seconds. So it's a very simple question, I guess, and the very basic. Yeah, this is the simple solution for this question. And what we have just discussed right now with the rate equation, we can simply solve such questions like this. And if it will be the first order, then the equation will change and the values will change. And if it is second order, then the equation will change. So we need to memorize the rate equations in all the cases, at least for 0, first, and second, and then we can solve these type of questions from these. I hope this is clear. Okay, so let's move forward, and this will be the last question for today's session. And in this case, if the concentration of N2 increases by 0.12 molar in 6 seconds, what is the average rate of appearance of H2O? So it's a kind of little bit different and what we have discussed, because we have discussed the equations right now. In this case, no equation will work, but you guys can try to solve this question. So they are asking about the rate of appearance of H2O. Okay, great. I got the answer. Okay, and the correct answer is C. Yeah, it's correct. Is 0.060. And how? Because when we look at the rate equations, it says that the rate of disappearance of NH3 quantity. And because there is 4, so we just simply write 1 by 4 here, is equal to rate of disappearance of 4 is equal to rate up, because here's the disappearance, so we are using negative, and because they are asking about appearance, so we just simply write d n2 by dt, and because it's 2, so it's 2, and it's 1 by 6, and appearance of H2O. So they should, and there they're asking about N2 and H2O, so we just need require these. So here the N2 is given as 0.12. So we just can simply put the values. So it's like 0.12. The time given is 6 and in here 1/6. And we need to calculate this rate of appearance of H2O. And when we simply add this and just cutting here, so we get this value which says is 0.06 molar per second. And the correct answer is C. I hope this question is clear to everyone. This is the last question of the session. And I hope the basic polymerization reaction, step growth, chain growth, different type of step growth, chain growth, their rates, and the equations involved in their rates and their conversion, their termination, we have quite clear idea about that right now. If any of you have any question regarding anything, I can repeat that again. And if not, then we can just move forward and to end the class. Okay, then I wish you guys all the best for week 6, assignment 6. I guess by these class, you will be able to solve the questions for week 6, assignment 6. And hope to see you in the next session then. Thank you for today.